Hello students, your physics teacher Hassan Darwish with you. In a new series of videos, I'm going to explain chapter 8, which is about the phenomenon of electromagnetic induction. And in this video, video 1, I'll make an introduction to this phenomenon. As usual, we start with the phenomenon of electromagnetic induction. The second, define the magnetic flux. State and apply the laws of induction. We mean Faraday's law, Lenz's law. Know the power distribution of the system, coil magnet. Coil magnet system. And finally, explain the phenomenon of alternators, explain the functioning of alternators and electric motor. Let's start. But before we start, as I write here, before we start explaining the lesson, see this experiment. This is an experiment made by someone or some teacher. Let's see it. Now in this experiment, you see here, we have a coil, okay? And this coil is connected to a wall outlet maintaining 220 volts sinusoidal. Clear? This is an iron bar. Here, another coil. Now to this free coil, we connected a small lamp. Do you see any generator here? You see any real generator, battery? No. Now, there is an electric current passing in this coil, which is variable. Let's see what happened. While you approach the coil with the lamp glows, though there is no generator, right? And the lamp glows. How this happened? Okay? So we are going to explain this experiment through the lesson. When we understand the phenomenon of electromagnetic induction. I made here the following two experiments. Let's see them. Here, in the first experiment, I have a coil. Good. Here I have a coil and a bar magnet connected to a microammeter. As you see, let me enlarge the figure. This is a microammeter. Now the microammeter measures very small current of the order of microampere. Do you see any generator in the experiment? No. Look here. When we approach the magnet introduced into the coil, the needle deviated towards the right, indicating the passage of an electric current. But where this current come from? We don't have any real generator, such as a battery. Clear? Next, or second, while the magnet is at rest in the coil, there is no movement of the needle, means the current is zero. You see, when we pulled the magnet away, the needle deviated in the other direction, means the current changed direction. You see, here returned to zero, deviated in the other direction. Let's change the polarity of the magnet. We do have an electric current, but in the other sense. Okay? Let me show you the second experiment. Here in the second experiment, this is called alternator. I have here a coil. Okay, you see, this is a coil connected to a pulley here because we want to rotate the coil inside a magnet, U-shaped magnet. Here is the U-shaped magnet, almost uniform magnetic field. Clear? Now the coil alone connected to a lamp. Here is the lamp. Okay? Here it is. Let's see what happens when we rotate the coil in the magnet. The lamp glows, although we don't have any generator, any real generator. No battery, no generator here. and the lamp glows. Clear? We are going to explain all these experiments. So let's start. Here's our coil in the first experiment. And here's our microammeter. The coil is connected to a microammeter. We don't have any generator in the circuit. No real generator. This is the bar magnet that we are going to move in and out of the coil. So move a bar magnet towards and away from a coil. The galvanometer connected to the coil shows electric current in the coil, but only while the magnet is moving. Okay? So galvanometer shows electric current, but only while the magnet is moving. When the magnet is stationary, means at rest, relative to the coil. The meter shows no current. Be careful about this. So current appears only when there is relative motion between magnet and coil. Also, the sense of the current depends on the sense of motion of the magnet. We observe this. You can review the video and see the experiment 1. Sense of motion of the magnet, and also on the nature of the pole nearer the coil, nature of the pole. Okay? This phenomenon is called electromagnetic induction. That is the appearance of electric current in the coil when there is a relative motion between the coil and the magnet. This phenomenon is called electromagnetic induction. The current is called what? Induced current. And the corresponding EMF means the maximum voltage. Okay? Remember this from first secondary, EMF, E. Clear? Which represent the voltage of the battery, U, when the current is 0. Remember this from first secondary. And the corresponding EMF required to drive this current is called induced EMF. Okay? Means that we don't have electric current if we do not have EMF in the circuit. Means a voltage. Now, interpretation. In order to be able to interpret this and other similar experiment, physicists defined a physical quantity called what? Magnetic flux. But what is a magnetic flux? Before I explain the magnetic flux, let me explain the concept of flux in general. What does flux mean? In reality, flux is something or any material crossing a certain area. Okay? Like one, for example, while water falling out of the tap, okay, this is called flux of water. Magnetic flux, here is our coil, and here is our microammeter or galvanometer. Here we have the magnet. And you know that magnetic field is represented usually by the magnetic field lines or magnetic spectrum. And you also know that inside the magnet, we consider that the magnetic field always from S pole to N pole. Outside the magnet, it is away from N toward S. Okay? Now the sense of lines. Clear? Let's move the magnet now. if you move the magnet into the coil, the number of lines crossing the area of the coil here, the face of the coil, increases, means the magnetic flux increases. First, I mean by the flux, the lines crossing this area represent flux, and we call it magnetic flux in this case. As you approach the magnet, the magnetic flux increases because the number of lines increases. If you move the magnet away from the coil, the number of lines decreases, which means that the magnetic flux decreases, okay? But in this case, and only in this case, while the flux increases or while the flux is decreasing, we observed electric current in the microammeter. So what does this mean? It means that the induced current or the induced EMF is only created when the flux in the coil either increases or decreases. While we observe that when the coil or when the magnet is at rest in the coil, means the magnetic flux is constant because the number of lines is constant. There is no electric current in the ammeter or microammeter. Okay? So the electric currents doesn't depend on the flux itself, depends on the increase or decrease of flux. I mean the variation of magnetic flux. Okay? This is everything in this video. In the next video, I'll explain the magnetic, or I will give you the rule of magnetic flux. Take care. Bye-bye.